All right, let's get going. Maybe the people from core will show up soonish. All right, new PRs this week. So as a result of our meeting last week, a couple of PRs landed for doing PG autoscaling for PG autoscaling changes. One from Miha to change the PG num to default PG num to 32 and the min as well. Let's see. There was another one that was in here, I thought, but I don't see it. I'll have to check and see. Anyway, let's see. There's another PR from Radic that changes encode for standard list T not to use buffer list copy in anymore. I haven't looked closely at this, but that does not surprise me that that would be a problem. So anyway, that might be interesting. Another one from Kifu. This is touches a ton of stuff, but use transparent comparator. So basically, avoid some extra work there. Loose store. Oh, and then Igor's really nice PR here that changes a couple of data structures that reduces the memory footprint of cached O nodes. This I did a little bit of testing on it. Well, Igor did a lot of testing originally, then I did a little bit more, but all of the tests seem to show that memory usage is reduced, both for reads and writes. Performance in some cases is improved, latency is improved. Maybe not a lot, but even in the case where you're not memory limited, there's still some reduction in overhead. So it's in general just a really nice win there. So that's exciting. Let's see, only one PR this week, performance PR this week closed that I could see. Just a doc change for OSD min PG log entries. That's another one that came out of discussion from last week. A couple of PRs got updated. Kifu reviewed this one for splitting read I/O if the I/O size is large for NVMe device. I'm not totally sure what the effect of that will be, but theoretically, hopefully they've tested it and it's good. Let's see, Adam's objection triumphant PR. It originally failed test, but it looks like it maybe was due to something else, not related to his PR, so it's back in testing again. Looking forward to seeing the results of that. Hopefully that means we can merge soon. RGW, the filtering logic to CLS that Eric added, it looks like that did pass QA, but needs rebased now. So that will need to be rebased. I don't know if it will need to go back through testing again or not, but that's good. Related to that, hopefully we can figure out if we can move some of the things that we need to filter on out of the data structure there so that we don't actually have to decode the entire thing in the CLS, but instead can just decode whatever we're filtering, then kind of reduce some of that overhead. But that was pre-existing prior to this PR, so it's not like it added anything new. See, objection sustained, that got updated and rebased, it looked like. And then other atoms, Blue Star sharding work that got some new changes based on a short review that we did. It was either last week or the week before, I think. So he's working on just simplifying a couple of things there before we merge that. So that was about it for this week so far. Oh, and perfect timing. It looks like some of the people from Core are starting to show up here. I think Miha was the one that wanted to discuss blue source space amplification. So maybe we can wait for her. Were there any PRs I missed or anything that folks wanted to talk about in the meantime? All right. Well, Igor, maybe you can, for folks who haven't been reading the mailing list, maybe you can talk a little bit about what you've been seeing with the blob space amplification that you were seeing in the testing you were doing.
Yeah. Hello, everyone. Yesterday I've been investigating space amplification for Azure-coded pools, mainly for BDKs, but it makes sense for other payloads as well. The driver for this investigation was a ticket from our customer who experienced up to 100% space overhead over the estimated volume. And actually I did some research, and it looks like, at least in pre-Octopus releases, one might have pretty significant space amplification up to 16 times theoretical upper bound when using Azure-coded pools over inner drives. And the reason for that is pretty large mean alloc size at booster level and, well, internal logic Azure-coded pools overrides. In Octopus, we currently have mean alloc size set to 4K, and this works around the issue. But at the same time, we are still thinking about maybe partial reversion this back to 16 or even 4K, as since larger allocation sizes are better from performance point of view. And hence we need pay some attention to this space amplification for Azure-coded pools I've just found. Primarily that's it. If you have any questions, then I'll be glad to answer.
Igor, how much of the effect that you saw was due to the blob wastage versus just the effect of having small objects with a larger min alloc size?
Well, I haven't investigated small object sizes in this analysis. So that was primary for RBD images, which tend not to have short objects. And
okay.
Actually, that's more about partial overrides. Some use patterns might have multiple allocations per 64K blob, and hence allocations, space amplification might be pretty high. So I provided some pretty simple and straightforward scenario to reproduce this. It's quite artificial, but more realistic scenarios can suffer from the same behavior as well, like pre-fill the RBD image and then partially override some OK extents, and you'll get on each, maybe not on each, but on each 4K override, which takes its own 64K range, you'll get another allocation without previous extent release.
Sure. So that's why your other PR won't fix this, the dynamic allocation size, even if you'd still be gaining a hint always for RBD to do a large.
It has nothing to do with the allocation size, right? The core issue with an erasure coded pool is that it's cloned, and so you can't overwrite current. So I guess it does that. It just means that you want to use a small allocation size, right? So for EC, we basically always want 4K.
Yep.
But actually, it might be a good point to, well, speaking about another MyPR which introduces flexible allocation sizes, and currently I'm suggesting to introduce a specific option for a pool, which is optimized for size or optimized for space, which is to specify behavior users' behalf. But probably we might consider using this optimized for space mode for erasure coded pool. It's mostly look like a workaround, but anyway, it's probably better than get this.
Yeah, I'm just trying to think. I mean, basically what this means is that if it's erasure coded, we always want to use 4K, right? And if it's SSD, we always want to use 4K.
That's what I tried to.
So the only question is like, what do we do with the spinner? And also, yeah, so if it's EC, we also always, it's a spinner and replicated. That's the only question, right?
Yeah, exactly.
Right. And so there, it really seems like this is a pretty narrow case, because if you get a big write, then we're going to do a big allocation, right? There's nothing really to do. I think the only question is, what do we do if we get a small write on a hard disk replicated pool and there isn't an existing, right? Am I thinking about this right?
Well, I'm thinking about the case when we have a pool of very small objects, which is not RGW, and maybe Ceph or something like that, or just a plain Redis pool. How we can tell BlueStore to use 4K allocation size in that case, or 64K otherwise. So we can't. First of all, we need to make the decision on the first write, because we can't mix small and large allocations.
For one object.
For one object, right?
Why?
So, because we have some, I recall unused bitmap. Probably depends on that, and maybe something else. So if you look at this PR with flexible minimal size selection, I need to provide, well, I need to persist this mode applied for this object, and I need to provide minlog size to number of functions
Yeah.
which can be
Well, I guess
right.
I'm not thinking about this in terms of min-alloc size because min-alloc size by definition is the allocation unit, and that is 4K, right? So it's not so much min-alloc size, it's how big we allocate our blobs. It's like how big do we allocate? That's actually the question, not min-alloc size, right? So if we get a large write, for example, then we'll do a large allocation. The question is how big do we allocate a small write? And by default, the current behavior is that we always allocate the smallest allocation, the smallest multiple of min-alloc size that's sufficient for a new write. That's the current behavior, and that's basically the crux of it. That's the thing that we might need to change. Because if you have, let's say you pre-fill an RBD image, and so it has a bunch of big allocations, and you do and a small write comes along, it's going to write into that same, it's going to do an overwrite, right? So there's no allocation anyway, and it's fine. So the only question is, what happens if we get a small random IO in a part of the image that hasn't been written yet? Do we allocate a small allocation, or do we do a large allocation and write only a small piece of it and set it to be unused?
Well, I can't tell exactly what happens there at the moment, but I recall that I decided that we are unable to mix of small and large allocations in a single object. Maybe we can revisit this, but it looked not that simple, if possible, at all. So some object or node structures depend on original on initial allocation size.
You mean initial min-alloc size or the initial allocation size? Because I mean, every blob a blob might be big, it might be small. Like it's all per blob thing. I can imagine that a blob.
Yeah, well, yeah, I had some ideas to try allocation size blob, and possible indeed, but for some reasons I decided not to go this way. But maybe this is possible, right? So, yeah, I'm not sure if that beneficial comparing to the complexity it brings. But
I guess I think I might be misunderstanding something. I'm not sure what is complicated. Because my understanding is this is how BlueStore has worked from day one, right? A blob can be big, it can be small. There's like a different write for do write big, and it has to decide how big the blob should be allocated. There's a maximum size, so that they aren't extremely big, but like they're always different sizes. Right?
That's correct for blob itself, but it's might be not correct for underlying physical extents it controls. Or maybe checksum chunks.
Yeah, right. The checksum order is the main thing that
unused
changes.
bitmap and things like that. But
yeah. So checksum order changes depending on the hint.
Probably you are right. It's technically possible in current design to have different allocation size for different blobs.
Not just technically possible, but like probably true of almost every object in the store that has had non-trivial IO patterns. Because if you have, say min-alloc size is 64K, you do a 384K write, and then you do 128K write, you're going to have two blobs that are totally different sizes. And then you do a 4K write, and it's going to do another 64K blob, and that's mostly empty, but has a 4K little spot filled in with unused bit set and all that stuff. If you change the whole,
we might get some side effects with blob reuse, which
Mm-hmm.
negate some complexity in this part, because right now we might rely on fixed location size for blob or fixed granularity for blob.
When you say might, it sounds like you're talking about a hypothetical change. Are you talking about what happens now, or are you talking about? I think I'm a little bit. Maybe I'm confused. Sorry.
Well, I'm just thinking of potential issues we might get on this path. For some, when I initially implemented this stuff, I might be dangerous sometimes, but no, maybe
I think that's the confusion. I'm not right now. I'm not talking about any path or any change or any pull request or anything. I'm talking about just what the current behavior is.
Current in the pull request, or
I don't even know which pull request we're talking about. I'm not talking about any pull request. I'm talking about current master, what it does today.
Well, for current code hardly depends on min-alloc size, which is fixed for BlueStore instance.
Right, exactly.
My PR brings some flexibility, and
are you talking about
about the PR with this flexible location size selection, and the idea to bring location size to make location size flexible at per blob level.
Right. Can we set the pull request aside for now and just talk about what currently happens and what we want to change? Because I don't want to. Let's just talk about first what the code does and what behavior we actually want to change, and then talk about possible ways that we can get that. But let's ignore the pull request for the
okay. Right now we have, I can say, maybe 3 issues. The first one, RGW, which keeps tons of small objects of spinner media, and hence we might, well, with 64K allocation size, we might get significant overhead.
But that's if we talk about current master, that's fixed because we have a min-alloc size of 4.
Yes, it's fixed occasionally, but at the same time we've got performance degradation for for writes on spinner-based pools.
So that's the second issue is that we have slower writes on HDD.
With this 60 with 4K min-alloc size.
Yes.
That
you said there are 3 issues.
Just talking. Before we move on to the other ones, though, can I ask, Igor, is that just general overhead though, due to? Yeah, I mean we know that.
Yeah, it just is a real problem for users. And what's the third problem?
Yep.
Is it that the erasure code?
The second use case is, well, it's similar to RBD, but some general purpose pool which contain plenty of small objects, and this differs from RGW case in a way that we can't control if objects are written in a single shot, or so in RGW we can say that small objects are written in a single shot, and this simplifies the handling. In general purpose pool, that's not true. So one might get the first small write and then large one. And hence we are unable to select proper allocation size on the first write.
Okay.
And the third case, which recently appeared, these are this Regia-coded pool shell overrides.
That's due to the shared blobs not being writable leads to a new allocation. Okay, so if we basically talk about current master, we changed min-alloc size to 4K, so all three of those issues are solved, right? Small RGW objects are small, and small objects written in pieces are still small. And the easy pool overhead is mostly gone because the allocation size, at least it's got as gone as it can be, given that we have to do the cloning and shared blob dance. Right?
Well, I'd say it's well, at least for GW, it's less visible. So one can imagine the case when just keeps one very small objects, but
like 1 byte objects.
Yeah,
It'll take 4K. Yeah.
I suppose we are fine with that overhead.
I think that's I think it's as good as it'll get for now, unless we inline it in the O node. But whatever. I think that's a separate discussion. So the only real problem I think 4K, just setting min-alloc size to 4K solves like 90% of our problems, right? On SSDs, we always want 4K. On erasure code pools, we always want 4K. For RGW, we always want 4K. The only problem is if it's a hard disk and it's RBD or CephFS, then maybe we want something bigger than 4K sometimes. Right?
CephFS is still going to have the space amp issues though, right? With small files?
Right. So sometimes you want 4K and sometimes you don't. Right. So RBD and CephFS on hard disks are the question mark.
Right. RGW is probably in the same suit because it might keep large objects, and it's a question what's the performance impact in this case.
Right. But if you have to do a large write with RGW, regardless of what min-alloc size is, it's going to do large allocations. Right?
You're going to hit a performance penalty with it, though.
Why?
From what
because
testing showed.
The bitmap's bigger? Or?
I was just basing it on what Igor's tests seemed to show when he did his last round of testing with 4K min-alloc. Probably because you're doing double writes, right, to the write-ahead log.
I didn't actually look at this.
Mind.
What was the actual test?
Never mind. Igor, do you have a link to your test results?
Maybe I'll send offline on Ceph.
Okay.
Because it seems like there's sort of there are two categories of issues here. One category is how big should our allocations be? Like if I get a small write, should I do a large allocation and write only a small piece of it because that's going to be better in the long run? Or if I get a small write, do I write to a small allocation? That's one category, like how big should I allocate? And the other category is like, is the allocator just behaving well, right? Like, if I do a large allocation, is it aligned so that when I do small allocations, things are less likely to fragment or, whatever it is. Like, I think there's stuff that could probably just be, or if I do a large allocation and there are both large extents free and small extents free, do I return the large extent or do I return a bunch of little extents mushed together? And that I think is just an allocator implementation question, the things that we could or maybe should improve if, I don't know what the current behavior is, but maybe that's like the second category of problem. Does that make sense? I guess I'm sort of assuming that the problem that we're facing right now is a question of how big do we allocate and not what is the what's the behavior of the allocator. But maybe that's a bad assumption. I'm wondering, do we know which is what we're facing here?
Well, what's about the following case? With 64K min-alloc size, we'll always have data the blob using 64K continuous chunks,
Mm-hmm.
and hence reads will benefit from this. But for 4K min-alloc size and partial overrides, you'll get fragmented blob. Well, you'll have fragmented 64K span.
Yep.
And this will result in lower reads.
Yeah, just because we're doing small allocations, right? So that feels like that's the first category of how big should I do my allocations? Because I can imagine that for RBD, for instance, say it's a completely empty image, we get a 4K random write that's in some random offset. The current behavior is 4K, that's a multiple of min-alloc size, and so I'm just going to allocate 4K. And so you're just going to get a tiny allocation, and then you randomly write the 4K next to it, and you'll get another allocation, and so on. Or you could say it's a 4K random write, but I know this is a block image, and I want to like reduce long-term fragmentation and so on. And so I'm actually going to allocate 64K, even though I only need 4K of it right now. But that's a decision that you have to make on that first write.
Right.
And as
actually,
yeah.
Actually,
Yeah.
what my PR partially does.
Partially done, right. So it's not so much a question of what min-alloc size is, it's a question of how big do I allocate when I have a small write. Like I think that's the question that we need to answer.
Yeah, probably you're
Okay.
right.
Igor,
But it could also be
Sage.
Sorry, just one sec, Mark. It could also be that there's
Sure,
a different issue. It could be that there's a different issue, right? It could be that I do decide to allocate 64K, but that 64K allocation I do isn't aligned to a 64K boundary. It's like shifted. And as a result, when I do, a million needed allocations and releases and so on, I get some fragmentation. Even though most of my allocations are big, my free space gets all screwed up or something like that, right? There could be some like secondary effect in the allocator behavior
Absolutely.
But it's not. But I think that's not really what we're worried about right now. I mean, we'll probably want to think about that later, but I think the real question right now is just how big do we allocate? I'm guessing when we get a small write. and it's really only for RBD and Ceph on hard disks for replicated pools. Like that's the only time it matters. The rest of the time, we always want to just do the smallest allocation we can.
Yeah, looks like that.
Sage, okay. the overhead there too, the space overhead, we're only talking about space overhead when you haven't filled that space, right?
Right.
It's not
exactly, yeah.
So it's not even like a case of like we're using way more than potentially the file would be, or that like range of an extent, or whatever you're talking about. It's only in the case where you just haven't done anything yet.
Yeah. Yeah, and I would actually say that in the case of RBD, like we basically always want to do slightly larger allocations because we don't have this sort of like small file issue. Like it's a block device and X of S is going to pack or not pack hot, but like I think we shouldn't get bent out of shape about that. We should assume it's sort of a sparsely but coarsely allocated chunk of space that file system is gonna do.
Yeah.
So I mean, even something as simple as if it's an RBD pool and it's rotational and it's replicated, then we should make the min blob size 64K instead of whatever it is right now, min-alloc size. And for RBD, I think that would basically solve. Well, okay, so here's actually the question. We keep talking about how it's slower. The min-lx size made something slower. What actually was tested and what actually was slower? Like what was
Look
the
at the
actual?
link, Sage.
Is it in your spreadsheet? Theory
This is
crafting?
Igor's. No, sorry, this is Igor's thing. I just posted a
In
link
your
in
pull,
the chat window. This was testing from a while ago. This was like
the
stuff
doc.
Igor did.
Got it.
Like,
Okay.
yeah.
Okay, so it's random right, RBD, 4K. Wait, so wait. So the red
Well,
ones are the
actually,
ones we care about?
that's standalone Blue Store. If you're writing randomly to some pre-filled store, so just a bunch of objects and partial overrides at random sets to these objects.
So what should I be looking at here?
Let me check.
What I was looking at was lines 35 and 36, columns B and C. That's master default versus master 4K, it looks like to me.
Yeah.
So massive default was the 64K before.
Right.
And this number is a percentage or is this an absolute number?
It's absolute number. It's megabytes per second.
Okay.
Actually,
So
it's better to use rows 52 and 50. From 40 to 54, as this covers the case when cache is off. And well, random writes, which is line 53, random write, and columns B and C.
But these are 4 meg reads and writes. Am I reading that right?
Yep.
Yeah.
So those are large sequential writes, basically got slower just by changing the allocation class.
Well, let me run through all the columns.
This looks totally different than what I assumed. I was assuming that the problem was with small writes, but this is actually saying that large writes changed performance significantly, like by half, just by changing.
Small writes are actually way faster because for small writes we basically are just doing sequential IO.
Okay, that's good. I'll accept reads are small writes, but reads are slower. So basically, okay, so this makes this sense. If we look at these 4 cells, basically, then, sorry. How to use a phone anymore. Writes get faster, but reads get slower. And that's just because they're smaller and spread out. So this here is probably with the small writes where we would want to do a larger allocation even though we don't have to for RBD. I think that what I was just talking about, that sort of makes sense. But this large write, do we have any idea why that's the case? Like why would a large write be like half as fast? Like less than half as fast.
Is it struggling to find allocation units large enough? Is this an allocator overhead problem?
Yeah, like maybe it needs a coarse grained bitmap or something.
Yeah.
I think this is the thing to look at. This is like problem, like sequential. Because on are there SSD tests here? Did they slow down for SSDs also? The streaming SSD writes also got slower.
Well, for SSD lines are from 4 to 18, and actually I don't see any
no real change
reduction in when using 4K.
But maybe it's
in some of the other tests that we've done, it was faster, actually.
So maybe it's non-contiguous or something. Like maybe
Yeah,
we're doing a 4 meg write and it's like allocating a bunch of little things.
yeah, I think something like that.
Okay. So it seems like this is the thing that we need to understand. Like what is actually going on? Because maybe from this, like just guessing, it seems like it's maybe a problem with the implementation of the allocator. Like Bluestore is probably asking for big blobs and the allocator is giving it little ones, a bunch of little ones, probably. Just something that the allocator should do different.
Actually, it doesn't care about giving contiguous space
The
for
allocator
booster
doesn't.
locations. It performs that for BlueFS rebalance, but for regular allocations, it doesn't care about
Sure.
contiguous allocations.
Yeah. See, that seems like that's the problem. Like that's the core issue, or at least the first core issue to address.
Yeah,
Right.
well, actually, we can try to fix that. Check what's happening.
I would suggest that we first just rerun these tests and then look at what's actually happening and try to understand what the change in behavior is. If in fact it is just getting smaller allocations, then we actually understand. At least we understand why. We can figure out how to make the allocator give bigger things.
Okay.
Pretty easy to confirm with like a block trace, right? Just to see what actually is happening on the disk.
Just look at the log and see how big the action requests are and how big the results are.
Sure.
On that, and then could compare it for the two, or even just look at the new case. That sounds like problem number one. And then problem number two is if we want to do something about the small write behavior where we're basically trading write performance for read performance. And that would be a more subtle thing where, here, I guess here. Or are you going to say something?
Oh, I was gonna go back and look. I thought we were better in both cases for small reads and small writes.
Well, small writes are faster, but small reads, because they're little things spread around, then they're slower. I think it makes intuitive sense.
Wait, what line are you on?
Line 20. Oh, I guess I'm looking at the wrong story. So line 22, writes got faster, and then line 26, reads got slower.
That's a range, isn't it? That's a range of 4K to 128K. If you look at just 4K, it's faster.
Oh,
than line 27.
Okay. That's only the range that got slower, but
So the larger IOs in that range are contributing are much slower. It looks like it must be.
Yeah. And maybe that's just because of that same allocator behavior that's breaking our large writes.
Yep.
And that actually makes sense because if you're doing like a mix of 4K IOs and like 128K IOs, then you're going to have a bunch of 4K holes, and then you do a 128K allocation, and it's going to give you like a bunch of.
No, I think this degradation for 128K is fragmentation as well. So
yeah,
we again get some fragmented stance and need to perform to seek proper.
Yeah. That's what I'm saying. So if that's the case, then it seems like there's basically one problem. possibly, or mostly one problem, and that's just that if there's a fragmented free space and you ask for a large allocation, the allocator is giving you little pieces. It doesn't know how to give you a big piece.
Yeah. Makes sense.
Okay. So way back when, God, it's been like 4 years now, whatever, when we were first talking about this, when we were talking about the bitmap allocator, we had this idea that there should be hierarchical bitmaps where there's the bitmap of the actual granular blocks, but then we would also have a coarse-grained bitmap that's like, I don't know, an order of magnitude more granular, less granular. That would either be completely free or completely used or whatever, so that if you're doing large allocations, you could efficiently find those large blocks. And if you're doing small allocations, then you would end up going down to the. Is that what we implemented, or does it not do that?
No.
Didn't implement that. Okay.
We have some hierarchies saying that underline span is completely free, and this might help in finding contiguous chunks, but it's.
That's what the leveled allocator does.
Yeah.
Like in the interior of the bitmap allocator, there are like multiple levels of different granularities. I'm almost certain that's what it's for.
But it got rewritten, right? Are you thinking of the original implementation, Sam, or the new one?
Whatever I read last month.
Okay.
There's two levels in the new one.
Okay.
Yeah, that's what I thought.
I mean, Igor's the expert there, though. He would.
Yeah, you wrote it right.
Well, actually, we might also want to try a new avail allocator here and check how it behaves.
Yeah.
I've seen pretty good performance results for it. I'm not sure if it wouldn't bring back this space memory
probably.
overhead issue, but from performance point of view, it's pretty good.
Maybe we should just try that to see. If that, just to look at this test, and it'll tell us a little bit more about what the core problem is. Okay.
Mark, question to you. Do you remember which cases were worse for min-log size in your benchmarks? Was it about large chunks as well?
So in my tests on NVMe, it was, I think we were like consistently better. I didn't do hard drive tests recently.
I see.
I've done them in the past, but in the past, back when I was looking at this years ago, the 4K min-log size, the biggest problem we had with it was encode decode of metadata. It was actually slower in all cases. Yeah, and now we've improved everything to the point where on Flash it looks like we're often better with a 4K min-log size in all cases, including small, where we then don't have to eat the write-ahead log overhead because we're doing this right.
So I think we have our line of investigation, right? We want to try the AVL allocator, see what happens, and also look at the bitmap one and understand what the allocations look like, and see if we understand what the core issue is. But I think we have to figure out. We have a decision point for Octopus, which is like close. If we want to stick with the 4K alloc size, or if we want to go back to 64, because I think what we're basically trading is with a 64K alloc size, then we have tons of space amp, but performance is better, at least for large writes. Whereas with the 4K alloc size that we have right now, then the space overhead issues go away, but large streaming writes are slower. But
Small random writes are faster.
random writes faster, yeah. And mixed writes are slower, right? It's like only the very small IOs that go faster.
Yeah, exactly.
Which is like, does that describe any workload ever? Like even the like realistic torturous RBD workload it's going to be a mix, right? It's going to be a mix of small and big. It's not going to be just small.
Yeah, probably. Unless you're doing something like crazy on it, right?
Yeah. Which basically means it's just slower.
Yeah.
If we traded Space Amp for performance.
So yeah, that's the big question, Sage. With the code the way it is right now, which hurts us more? Specifically with hard drives.
I think that the optimistic case is that we can get to the bottom of the allocation issue and we can make some change to the allocator that'll improve things.
Yep.
But I think that's optimistic given our timeline.
Well, actually, it's pretty easy to request contiguous chunks from bitmap allocator right now.
Okay.
Because it already has this mode for BlueFS, so might be easy to try.
They could just try a large extent allocation if that fails, or tries a contiguous if that fails, and it tries a non-contiguous.
This part needs to be implemented. Right now on a single call it might provide contiguous chunk or fail, but you can call it second time and specify that you don't need contiguous allocation anymore, and it will.
It sounds expensive, but for if we only did that for hard disks, then it would probably be fine.
Yeah.
Or you could probably pass a flag in or something to do that. So maybe that's.
Well, potential issue with this behavior is that over the time space might be fragmented and the overhead to search contiguous blocks might be higher.
And fail every time.
And
that would be more likely to be the case after lots and lots of I/O, right? Once you've kind of gotten fuller.
And aged.
In almost full devices after high load.
Presumably,
unfortunately, we are not good in benchmarking such cases in lab because, well, several months of production work they might result in completely different data layout on the disk.
The times I've done stuff like that, it's not looked great already. We slow down pretty significantly once we see a lot of fragmentation and full disk. Maybe though, in conjunction with this, we think about background defrag.
Well, this definitely wouldn't fit in Octopus.
Yeah. So it sounds like we want to investigate, try to make sure we understand the problem, and perhaps try out like a quick fix.
Yeah.
But I think we should also be prepared to revert back to 64K man-Alex size for hard disks for Octopus if we don't sort of solve this.
It's hard.
Yeah, I think that's that's safe, realistic option.
Should we just do that now? And then if we like have solve this, crack this nut, then we go back?
I mean, I don't mind it. I mean, we are all in agreement for the SSDs. It's 4K makes sense, but for hard disks, if we know that there is potential problems all over the space, then we should just go back to 64. And if we have a solution in time, we can.
We can go back. Yeah.
Yeah.
Which is good about my PR. If we simplify it a bit, we can have the flexibility to switch back and forth in this behavior.
I would advocate that we use Igor's PR rather than switching completely back, if we can do that.
But I think that Igor's PR is, your PR doesn't change the allocator, and the core problem is that when you ask for big extents in the allocator, it gives you little ones, isn't it? Or is it actually calling the allocator differently?
Yeah.
I don't think your PR is related to the actual problem.
Yeah.
I thought if we used his PR though, we would get that kind of dynamic behavior where we can use small.
No. Well, wait. For optimal, so if you tag the pool as to optimize for speed, it will choose 64 min-alloc size. It will provide it to allocator, and this will require allocator to return contiguous chunks. So this becomes almost the same as we just have default min-alloc size at 64K.
So it's basically just it's setting min-alloc size to 4K, but it's requesting 64K at a time and setting that flag that says it has to be a contiguous.
Yeah.
Is that what you're saying? Okay.
Yeah.
So that also, I think that also makes me nervous until we understand what the allocator behavior should be, because that has the risk of, with an aged store, like just wasting CPU because it has to do this search. Like it seems to me that if we want to do something, the conservative thing would actually be for hard disks, create the store with min-alloc size of 4K, but have a flag on the allocator that says you're required to actually do 64K multiple allocations for the whole device always, just so that the disk format is the same. And so when we eventually fix this, those OSDs are still okay.
Yeah.
But like maybe that would be sort of the stepping stone.
Well, actually, it's possible to downgrade or upgrade, or whatever you call it. So it's possible to move from 64K to 4K, but it's not possible to go back.
Go the other way, yeah. And that's not implemented, right? I think there might be some subtle effects in the data structures.
Well, again, you should, each node currently has to know allocation size it was created with.
Yeah. That feels like it's in the category of theoretically possible, but also complicated and not implemented. It'd probably be easier to like if you really are worried about these like OSDs created with a fresh Octopus release being able to benefit later, just hack the allocator. Or not even the allocator, actually just the free list manager. It's actually the free list manager.
Yeah.
Whatever.
Yeah, do something like that. Anyway.
Question for Josh before we move on. Josh, there's a specific customer I'm thinking of that has erasure coding, and they're doing very small RGW object writes. And my question for you was just, do you know if they were on hard drives or not?
The one you're thinking of is not. I'm sure others are, though.
Okay. I was wondering specifically about the space amp issue there and how much, if we see it on hard drives, if we see people doing this, like really small erasure coded RGW objects.
We definitely do. And they have a lot of overhead just purely from the use of EC in that case, combined with the min-alloc size. But the move to 4K for SSD a lot for that, at least those users who are using SSDs.
On the hard drive side, do you think that they would prefer to have less space amp or more performance on the writes, on large writes?
That's a good question. For hard disks users, I would expect they're less performance sensitive than space amp sensitive in that case.
Okay.
The nice thing about the RGW small writes, though, is that we know that the object size is going to be 4K or whatever small size it is when we're writing it. It's not going to change. So if we did have this, like the disk layout in 4K min-alloc size blocks, and when we're doing immutable writes, perhaps we could use that as a key like eCruisePR does to allocate smaller chunks for those, but still let you use like larger sizes for RP.
Sure. Yeah, what do you think about that? That's my concern with this, is that if we move back to 64K, we might gain the performance back, but I'm worried both with the space amp and then also being able to, like, in the future, do things like what Josh and Igor are talking about here.
So if I have to put it simply, I think we are going to improve things for customers who are using SSD. We are not changing anything for customers who are using hard disks. We can live with that as long as we're saying that we're making forward progress towards that in a later release, or like even a later Octopus point release. So as long as we're not going worse, I'm fine with that.
In terms of like
Because
space amplification?
No, I mean, yeah, if we go back to 64K for hard disks, we just go back to what we were, right? Even in Luminous or Epic or Nautilus or any customer running any version.
Okay, so the problems with space amplification that people are running into right now isn't too bad. It's like okay.
Well, actually, I've seen several complaints about this couple for our customers, and some in. So it exists, I'd say.
Yeah, I mean, sure, it definitely does exist, but when we are trying to make a decision, we should be careful about what we're trying to do, right? I mean, we've optimized for the SSD case. That's good. But for the hard disk case, if we want to make a decision, we should make a decision which is foolproof for all workloads, all kind of scenarios. And I think what we just discussed in the last hour makes sense, because if we are able to make small changes in the allocator code and get benefit out of it, we should do that, rather than taking a hard decision and like setting wrong defaults for hard disks as well.
Well, but Neha, right? That change would go in conjunction with the smaller min size, right? Like we do both at the same time. If we can't do the allocator changes, then I guess we'd revert back to the 64K min size if we don't want the performance benefit. Is that
no? I'm just saying that worst case scenario, what we are able to do with Octopus is that we go down to like 4K. What we've already done for master, we just go up for hard disks, which is 64K, which is literally what we were doing for the hard disks case. We are not changing anything, is what I'm trying to say. In future, we know that it is a problem, and what Igor is going to investigate will get us to a better solution, is what I'm trying to say. But until then, we shouldn't make any changes there. What I'm trying to across.
So then potentially in the future, if we left the min-alloc size at 64K, we would still be stuck with Octopus clusters at a 64K min-alloc size, which we might not then be able to utilize the allocator changes, right? unless we did a conversion.
Yeah,
That's true for
Does that
any
make
existing
sense?
cluster, though, Mark.
that's
All
true
Postgres
for,
clusters today.
Yeah, exactly. It just, the only difference would be then new Octopus clusters would potentially benefit, right?
Yeah,
Yeah.
potentially. But I think we'll need a way to either just redeploy OSDs, or maybe we can make some kind of easy migration path than that for existing clusters anyway.
Okay. Igor, do you have the time to look at the allocator and try to see if we can do the contiguous allocation?
I'll do my best. I'm not sure about having plenty of time, since I need to do some work before Cephalacon. But I'll do my best.
Josh or Nihat, do you know when the window for Octopus is?
Looks like they have left. Octopuses are trying to kind of close things down for next couple of weeks, and then they start concentrating on bug fixes.
Okay. So maybe if it's looking like it's going to be rough over like the next 2 weeks or something, maybe then if we can't figure anything out by then, do we revert? Is that a reasonable plan? Just for hard drives?
Yeah, just for hard drives reverting to 64K seems like the reasonable thing. We can't
Okay.
figure out a fix.
Okay, so I'll put in the discussion notes here. When's our deadline to figure this out?
Yeah, let's say a couple weeks. We want to have enough time to make sure whatever we come up with is tested enough that we are confident in it for Octopus.
Let's see here. Would that be like February 7th? Is that like 2 weeks? Is
Yeah.
that a reasonable date? Okay. By 2/7/2020, convert HDD and Alex size 264K.
And by the way, this is also something that we could probably end up backporting if we do find the fix for the allocator later.
Sure. All right, cool. I think we've gone like 15 minutes past the end time for the meeting. So anything else, guys? All right. Have a great week, everyone. See you next week.
See you.
Thanks.
Bye.
See ya.